Welcome! In today's session, we'll tackle the problem number 702, search an assorted array of unknown size. This problem focuses on efficiently searching within a sorted array when its size is unknown, using the array reader interface. It's a great opportunity to enhance your problem-solving skills and think critically about algorithm design. Let's dive in. The problem we're solving involves an integer array, RR, that is sorted in ascending order and contains distinct values. Importantly, the size of the array is unknown. Along with this array, you're also given an integer target, and the goal is to determine the index of target in the array, or return -1 if the target doesn't exist. However, you cannot directly access the array. Instead, you have to interact with it through an array reader interface. This interface provides a single method, getIndex, which retrieves the value at the specified index in the array. If you attempt to access an out-of-bounds index, the interface will return the value 2*31*1. Keeping these constraints in mind, your task is to implement a function, search, that takes the array reader instance and the target as inputs and efficiently returns the index of the target, or -1 if it's not found. To better understand the problem, let's look at a concrete example. Suppose the array ARR is -1, 0, 3, 5, 9, 12, and the target value is 9. In this case, the function should return 4 because the value 9 exists in the array at index 4. On the other hand, if the target value is 2, the function should return -1 since 2 is not present in the array. This highlights the two possible outcomes: either the index of the target is returned, or -1 is provided when the target doesn't exist. Now, consider another example where the target is 12. In this case, the function should return 5 because the value 12 is located at index 5 in the array. These examples illustrate the expected behavior of the function. Keep in mind that the array is sorted, and all its elements are distinct. This sorted nature is something we can leverage to design an efficient solution. However, the primary challenge lies in the fact that the size of the array is unknown, and you can only access values through the array reader interface. There's one more critical detail about the arrayReader.getIndex method. If you attempt to access an index that is outside the bounds of the array, the method will return the value 2*31*1. This serves as an indicator that you've gone beyond the array's limits. It's important to account for this behavior when designing your solution, as it ensures your function doesn't rely on knowing the array's size upfront. With these constraints and examples in mind, you're tasked with devising an efficient algorithm to find the target's index or determine that it doesn't exist. To begin solving this problem, one intuitive approach is using a brute force method, specifically a linear search. The idea here is straightforward: since the array is sorted, we can iterate through it sequentially, beginning at index 0. We use the arrayReader.get function to fetch each element. If the value matches the target, we return the index. If the value exceeds the target, or if the arrayReader.get function indicates we're out of bounds by returning a large sentinel value like 2^31*1, we terminate the search. While this method is simple to implement, it has some significant drawbacks. The time complexity is O(n), where n is the number of valid elements before we hit the out-of-bounds marker. This makes it inefficient for large arrays. Additionally, because we're accessing each index sequentially, it doesn't take advantage of the fact that the array is sorted, which means we're missing an opportunity to optimize the search process. Overall, while linear search is a basic and universal strategy, it's not well suited for this problem, especially when dealing with larger datasets or when efficiency is critical. Now, to address the inefficiencies of linear search, we can turn to a more optimized approach: exponential search combined with binary search. This method is designed to efficiently locate the target in a sorted array of unknown size. The key insight here is to first identify a suitable search range using exponential search. Starting with an initial range of 0, 1, we progressively double the upper bound of the range until the value at the upper bound exceeds the target or we encounter the out-of-bounds condition. Once we've identified an appropriate range, we can then apply binary search within this range to pinpoint the target's exact position. This approach is highly efficient, with a time complexity of O log n. The exponential search step takes O log n to determine the range, and the binary search within that range also takes O log n. The space complexity remains O1, as no additional storage is required. While this method is more complex to implement than linear search, it smartly leverages the sorted nature of the array to drastically reduce the number of comparisons and array reader calls, making it a far better choice for large datasets. Given the constraints of the problem and the need for efficiency, we've chosen the exponential search combined with binary search approach as our strategy. This method is both scalable and efficient, as it minimizes the number of calls to the array reader interface while guaranteeing the correct result. The key observation driving this choice is that exponential range expansion allows us to quickly isolate a potential search window, even when the size of the array is unknown. From there, binary search effectively pinpoints the target within the narrowed range. Linear search, while simpler, is impractical for large arrays due to its O(n) time complexity. In contrast, the combination of exponential search with binary search balances rapid range identification and precise targeting, resulting in a logarithmic time complexity overall. Although this strategy requires careful implementation, it offers the best performance for this problem. By leveraging the sorted property of the array and reducing unnecessary comparisons, we ensure an optimal solution that scales well, even for very large datasets. In this problem, we're tasked with finding the index of a target value in an infinite sorted array. The challenge here is that the array doesn't have predefined bounds, and we can only access elements through an array reader interface. This interface allows us to retrieve the value at any index I using arrayReader.get I. If the index exceeds the bounds of the array, the interface returns a large sentinel value, such as 2 to the power of 31 Now, one straightforward way to solve this is by using a brute force approach, specifically linear search. The idea is simple: we start at index 0 and sequentially check each element. If the current element matches the target, we return the index. If the current value exceeds the target or hits the sentinel value, we stop, as further elements will only be larger due to the array being sorted. While this method is easy to implement, it's inefficient for large arrays since it requires checking each element one by one. Edge cases to consider here include scenarios where the target doesn't exist, the array is empty, or it contains very few elements. The sentinel value helps us handle these cases gracefully by signaling when we've gone out of bounds. The brute force approach comes with a time complexity of O(n), where n is the index of the target value in the array. This makes it inefficient for large arrays as the number of steps grows linearly. On the other hand, the space complexity is O(1), as we don't use any additional data structures. To improve efficiency, we can turn to an optimized approach that combines exponential search with binary search. This method leverages the sorted nature of the array to avoid unnecessary comparisons. First, we use exponential search to quickly identify a range where the target value might lie. Starting with low equals 0 and high equals 1, we double the high index until the value at arrayReader.get high exceeds the target or we encounter the sentinel value. For example, if the target is 35 and the array is 1, 2, 5, 10, 20, 35, 100, we would expand the bounds as follows. At high equals 1, the value is 2, which is less than 35, so we continue. At high equals 2, the value is 5, so we continue doubling. At high equals 4, the value is 20, and we double again. Finally, at high equals 8, we encounter the sentinel value, so we stop. This process gives us a range, such as 4, 8, where the target must lie. Once we've identified the range using exponential search, we narrow down the location of the target using binary search. Here, we perform a binary search within the range low, high. We calculate the midpoint mid equals low plus high ///2 and compare arrayReader.get mid with the target. If the value at mid matches the target, we return mid. If the value is greater than the target, we update high equals mid 1 to search the left half of the range. If the value is smaller than the target, we update low equals mid plus 1 to search the right half. This process continues until either low exceeds high, which means the target is not in the array, or we find the target. With this approach, edge cases include handling arrays where the target doesn't exist or when the array size is very small. The combined time complexity for this method is O log n, where n is the index of the target. The exponential search phase takes O log n to find the bounds, and the binary search within the bounds also takes O log n. The space complexity remains 1, as we only use a few variables to track the search range. The combination of exponential search and binary search is key to solving this problem efficiently. Exponential search quickly identifies a range where the target might be, leveraging the sorted nature of the array while avoiding the inefficiency of a full linear search. This phase ensures that we don't waste time searching through elements that are guaranteed to be out of range. Once the range is identified, binary search allows us to zero in on the target with minimal comparisons. This two-step process is particularly effective for infinite arrays, as it avoids the need to know the size of the array in advance. By doubling the index during exponential search, we approximate the bounds of the array dynamically. The array reader interface plays a crucial role here, as it provides an efficient way to access elements without requiring full access to the array's contents. Variables like low, high, and mid help define and refine the search range, making the process systematic and efficient. This approach includes several optimizations to ensure efficiency. The exponential growth in the first phase minimizes the number of calls to array reader, making it scalable even for very large arrays. The use of the sentinel value as an out-of-bounds indicator simplifies the implementation, avoiding unnecessary comparisons. By combining exponential search and binary search, we achieve a time complexity of O log n, which is optimal for searching in a sorted array. This method is not only efficient but also robust, as it gracefully handles the constraints of an infinite array. In summary, the solution efficiently leverages the sorted property of the array and the capabilities of the array reader interface to find the target index with minimal overhead. It's a scalable and elegant solution to a challenging problem. In this Python implementation of LeetCode problem 702, we aim to find the index of a target value in an infinite sorted array, accessed through the array reader interface. The solution begins by determining the search bounds. Since the array is infinite, we cannot use a fixed range. Instead, we start with left equals 0 and right equals 1. We then expand the bounds exponentially by doubling the value of right until the target is within the range, i.e., until reader.get right equals target. This ensures the search range encompasses the target value without traversing unnecessary indices. Next, we perform a binary search within the determined bounds. The while loop runs as long as left equals right. Inside the loop, we calculate the middle index with mid equals left plus right left //2, avoiding potential integer overflow. We retrieve the value at this index using reader.get mid. If the value at mid equals the target, we return mid as the index of the target. If the value is greater than the target must be in the left half, so we update right equals mid 1. Conversely, if the value is less than the target must be in the right half, so we update left equals mid plus 1. If the loop exits without finding the target, we return -1, indicating that the target is not present in the array. This implementation is efficient, with a time complexity of O log n, for both the range determination and binary search, where n is the position of the target in the array. The exponential expansion ensures that the algorithm adapts dynamically to the unknown size of the array, making it suitable for this problem's constraints. In this solution, we're tackling the problem of searching in a sorted array of unknown size. To begin, we define an interface called ArrayReader, which has a single method, get, that retrieves the value at a given index. This is essential because the array size is unknown, so we can only access elements using this method. Next, we define the search method in the solution class. Here, we start by initializing two pointers, left and right, to represent our search bounds. Initially, left is set to 0, and right is set to 1. The idea is to exponentially expand the search bounds until the target value lies within the range defined by these pointers. This is achieved by repeatedly checking if the value at the right pointer is less than the target. If it is, we shift the left pointer to the current right, and then double the right pointer. This ensures that we quickly cover a large portion of the array while narrowing down the region where the target might exist. Once the bounds are correctly identified, we transition to a binary search phase to efficiently locate the target within the determined range. The binary search starts by calculating the midpoint of the current range using the formula mid equals left plus right minus left divided by 2. This approach avoids potential integer overflow issues. We then retrieve the value at the midpoint using the reader.get method. If this value matches the target, we return the index mid, as we found the target. However, if the midpoint value is greater than the target, it means the target lies in the left half of the current range, so we update the right pointer to mid-1. Conversely, if the midpoint value is less than the target, we move the left pointer to mid+1, narrowing the search to the right half. This process repeats until the left pointer exceeds the right pointer, indicating that the target is not present in the array. In this case, we return -1 to signify that the search was unsuccessful. Let's start with an example where the target value is present in the array. The input consists of a sorted array represented by the reader object, and the target value is 9. To begin, we need to determine our search bounds. We initialize left to 0 and right to 1, then check if the value at reader.get right is less than the target. At right equals 1, the value is 0, which is less than 9, so we update left to 1 and double right to 2. Now, reader.get 2 gives 3, which is still less than 9. We update left to 2 and double right again to 4. At this point, reader.get 4 equals 9, which matches the target, so we stop expanding the bounds. With the bounds established as left equals 2 and right equals 4, we proceed to perform a binary search. The midpoint is calculated as mid equals 3, and reader.get mid returns 5. Since 5 is less than 9, we update left to mid+1, which is 4. Recalculating the midpoint gives mid equals 4, and reader.get 4 is 9, which matches the target. Therefore, we return the index 4 as the result. Now let's consider an example where the target value is smaller than all the elements in the array. The target is -5, and the array starts as before. First, we need to determine the search bounds. Again, we initialize left to 0 and right to 1. Checking reader.get 1, we find the value is 0, which is greater than -5. Since the value at right is already greater than the target, we stop expanding the bounds. The bounds remain left equals 0 and right equals 1. Next, we move to binary search. The midpoint is calculated as mid equals 0, and reader.get mid returns -1. Since -1 is greater than -5, we update right to mid-1, which becomes -1. At this point, left is greater than right, which indicates that the target is not present in the array. As a result, we return -1 to signify that the target was not found. In this example, the target value is larger than all practical elements in the array. The target is 100, and the array remains the same. To start, we determine the search bounds by initializing left to 0 and right to 1. Checking reader.get 1, we find the value is 0, which is less than 100. So, we update left to 1 and double right to 2. Next, reader.get 2 gives 3, which is also less than 100. We update left to 2 and double right to 4. Then, reader.get 4 is 9, still less than 100, so we update left to 4 and double right to 8. At right equals 8, reader.get 8 equals the large predefined value of 231-1, which is significantly greater than 100. Since we've encountered this large sentinel value, we stop expanding the bounds. The bounds are finalized as left equals 4 and right equals 8. With the bounds determined, we proceed to perform a binary search. The midpoint is calculated as mid equals 6, and reader.get mid returns 231-1. Since 231-1 is greater than 100, we update right to mid-1, which becomes 5. Recalculating the midpoint gives mid equals 4, and reader.get 4 is 9. This time, 9 is less than 100, so we update left to mid+1, which is 5. Calculating the midpoint again, mid equals 5, and reader.get mid returns 12. Since 12 is still less than 100, we update left to mid+1, which becomes 6. At this point, left is greater than right, which means the target is not found in the array. Therefore, we return -1 as the final output. In this algorithm, the time complexity is determined by two key steps, the exponential bound search and the binary search. To start, the exponential bound search is used to locate the range where the target might exist. Here, we initialize left to 0 and right to 1, and then repeatedly double the right boundary until the value at that index is greater than or equal to the target. This doubling process ensures that the search expands exponentially, covering indices like 1, 2, 4, 8, and so on. If the target is located at an index k, this step takes approximately log 2, k, iterations, because we're essentially finding the smallest power of 2 that exceeds k. This gives the exponential bound search time complexity of O log k. After the range is identified, we proceed with binary search. Since the range is proportional to k, binary search will also operate with a time complexity of O log k, as it systematically halves the search range at each step. Together, these two steps provide the foundation for this algorithm's efficiency. When we combine the time complexities of both steps, we get the overall time complexity. The exponential bound search contributes O log k, and the binary search also contributes O log k. Adding these together results in O log k plus log k, which simplifies to O log k. This shows how efficiently the algorithm narrows down the search space. Now, let's look at the space complexity. The algorithm uses only a constant amount of additional memory. Variables such as left, right, mid, and min_value are reused throughout the process, and no auxiliary data structures are required. Since the algorithm operates in place without allocating extra memory, the space complexity is O1. This combination of logarithmic time complexity and constant space usage makes the approach both fast and memory efficient. To better understand the algorithm's performance, we can analyze its behavior in different scenarios. In the best case, the target might be found during the early iterations of the exponential bound search or right at the start of the binary search. Even in these situations, the logarithmic growth of the search space means the complexity remains O log k. In the average case, where the target is located somewhere in the middle of the array, the algorithm still performs O log k operations in both the exponential search and the binary search, resulting in an overall complexity of O log k. Finally, in the worst case, where the target doesn't exist in the array, the algorithm still needs to execute O log k steps to determine the bounds and another O log k steps to confirm the absence of the target during binary search. Regardless of the scenario, the algorithm consistently achieves a time complexity of O log k. It's helpful to compare this optimized approach to a naive method. A brute force solution would involve iterating through the array sequentially until the target is found or the array ends. This has a time complexity of O k, where k is the index of the target or the size of the array if the target doesn't exist. However, the space complexity for this approach remains O1. In contrast, the optimized method of combining exponential search and binary search dramatically reduces the time complexity to O log k, while maintaining the same space complexity of O1. The key advantage lies in the logarithmic reduction of the search space. By leveraging exponential growth to quickly locate the bounds and then applying binary search within that range, we achieve an optimal balance of speed and memory efficiency. This approach is particularly well suited for searching an assorted array of unknown size, as it ensures the fastest possible resolution given the constraints. When working on this problem, there are a few common mistakes to watch out for. First, many candidates forget that the input array is sorted. This is critical because it means you can use binary search to achieve an efficient solution with O log n complexity. Ignoring this and resorting to linear search leads to a suboptimal O n solution. Next, remember that the array reader interface does not allow direct access to the array elements. You must retrieve values using the get method. Attempting to directly access elements, such as with arr_i, will result in invalid solutions. Another issue is failing to handle out-of-bounds access. Since the array size is unknown, accessing indices beyond its range can lead to errors. Always account for this when using arrayReader.getIndex. Finally, avoid assuming fixed bounds for your binary search. For example, defining bounds as 0 to n1 may fail since the array size is unknown. Instead, dynamically determine the search space to handle edge cases effectively. Overcomplicating the solution is another pitfall. Some candidates add unnecessary preprocessing steps or auxiliary data structures, which increase complexity and deviate from the optimal O log n solution. Stick to binary search principles for simplicity and efficiency. In interviews, it's important to recognize recurring patterns, such as leveraging binary search for sorted arrays. Pay attention to unique constraints, like unknown bounds or limited access methods, as these are common in interview scenarios. Edge cases are also crucial. Be prepared to handle situations like empty arrays, single-element arrays, or cases where the target value is outside the range of all elements. Additionally, aim for optimal space complexity. Most binary search problems do not require extra space, so only use additional structures if explicitly necessary. Lastly, communicate your approach clearly, especially how you dynamically set bounds when the array size is unknown. This demonstrates logical thinking and clarity, which interviewers highly value. To build a stronger foundation, it's helpful to practice related problems. For instance, LeetCode 704 is the fundamental binary search problem and is essential for mastering the basic mechanics. LeetCode 702, the problem we're discussing, introduces constraints like unknown bounds, reinforcing the need to adapt binary search. Then, there's LeetCode 33, which involves searching in a rotated sorted array. This adds complexity and is great for enhancing your problem-solving skills with binary search variations. Finally, LeetCode 74 extends binary search to two-dimensional arrays, which helps you think about applying binary search in different contexts. Tackling these problems will deepen your understanding and prepare you for a wide range of scenarios. There are also alternative approaches worth considering. One is exponential search, which is particularly effective when the array size is unknown. This method involves doubling the index range to find the appropriate bounds for binary search, preserving the log n complexity. While slightly more complex to implement, it's invaluable for dynamically determining bounds. For very small arrays, a modified linear search can sometimes be competitive with binary search. However, this is generally inefficient for larger inputs and is only advisable when simplicity is a priority over performance. Another option is recursive binary search, which some candidates find more intuitive than the iterative approach. However, iterative solutions are usually preferred, as recursion can lead to stack overflow in languages with limited recursion depth. While recursive methods may be easier to write, they come with additional memory overhead due to function call stacks. Understanding these trade-offs helps you choose the best approach for the problem at hand. Great job! Today, we learned how to search an assorted array with an unknown size, leveraging binary search for efficiency. Remember the importance of understanding constraints like limited access to the array. Keep practicing and applying these techniques to similar problems. Thanks for joining, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!